Well, this is a short recording on how to handle functions of more than one variable so that the differentiation rules that you learned in a Principles of Calculus course can be applied to more interesting and more complicated functions. Let's start off with taking an example that you already know about. Here's a simple equation. And if you were asked to take the derivative, compute the derivative of that function in calculus class, that's something that should be easy to do. What you do is you compute using the operator here, or the notation, the change in y with respect to x. And you know from the rule for calculating the derivative of a polynomial that this is 6x minus 2. There are lots of examples of how to do this, but let's take a second to talk about the notation. Sometimes functions are labeled as f of x, a function of x, instead of y. So our function would be written f of x equals, let's take another example, the natural logarithm of x. In that case, you could find the derivative of f with respect to x, and that would be 1 over x. Or you could say f prime is equal to 1 over x. Now, what if the function that you were operating with had more than one independent variable? After all, to be interesting in economics, most of the interesting functions have more than one independent variable. We know demand functions depend not only on price but also on income and the prices of other goods. We know that cost functions depend not only on output but on input prices and the technology measured somehow. How can we compute derivatives in the cases where the function involved has more than one independent variable? Well, let's take a simple example, again a polynomial, and we can try and write f of x and z. X and z are our two independent variables, and we can write a simple polynomial. Let's write 2x z squared. Now, what would it mean to take the derivative of this function with respect to x? Well, in calculus class, to compute the derivative of this function f, which we could call this y. In order to do this in calculus class, the standard solution is to consider all of the other variables than x, in this case just z, as constants when you take the derivative. And in order to denote the fact that there's more than one independent variable in the equation you're differentiating, mathematicians use a special symbol that's called the symbol for partial differentiation. It's kind of a twisted around d. So we can say dy x here is equal to 2z squared, treating z squared as if it were a constant, just as 2 is a constant in this equation. And because there are two variables on the right-hand side, we can compute dy dz. In this case, we have to treat x as if it were a constant. So we would have 2 times 2x z. And we call this the partial derivative of y with respect to z. This is the partial derivative of y with respect to x. This gives us the groundwork for differentiating functions and finding things like elasticities and slopes and marginal values in a wide range of economic functions.